Now let's discuss about the second pattern, which is scaling rights. So it's just the quite opposite of what we have discussed in scaling reads. So here basically it tries to address the challenge of high volume write operations. When when our single server or single database truly becomes a bottleneck in overall of our design. So if our application grows from hundreds of writes to few thousands of writes to millions of writes per second, then this individual servers or databases that we have, it will hit hard limits on this disk input output, CPUs and network bandwidth and all that stuffs. So that is where if that situation is kind of something that we are thrown into, so what are the solutions or the approaches that we can think of, and how can we adopt them as if we try to implement specific design. So that's the pattern. So let's try to see if we can how it evolves and all. So here the scaling rights, the problem is like I just mentioned. So during high writes per second, so assume this is a graph of the write throughput versus the time. So as with time, if more writes are hitting our server, that's when actually it will be the bottleneck for our server or a database. So these are the situations how do we deal with. So let's see the approaches that we can come up with. So the solutions, so to handle this kind of situation, there are a few approaches, and then we'll try to elaborate one at a time as we keep diving deeper into each of the approaches. But let's try to have a quick look at what are each approach is. So first one is vertical plus database choices. So here trying to like bigger hardware, so I'll talk about more on that. So and then the right optimized database, trying to choose the right ones, the database that is specifically built for kind of system that we are building. So that's one thing to look for immediately. Then the other way is basically trying to shard and partition. If you remember, we had a brief discussion of sharding in scaling rates. That was just one of option in scaling rates, but ideally that's not adopted in to solve the problem of reads. Mostly it's adopted to solve this writes traffic. So here this is where sharding is also one of the options. That also it has horizontal sharding and then vertical partitioning and all. So that is the second option. The other is basically we have an option of queuing plus shedding. So here we'll try to to handle the spike of a traffic, we'll try to introduce a queue in between our server and application, so that handles a spike of traffic, and it each will be picked up by our workers or whatever it is. So that's one way. And shedding is basically trying to see if we can reduce the unwanted request, and only basically let's say we have a server which is keeping track of the likes or counts for our videos or posts or whatever it is. So it's not necessary that we need to 100 people is liking it, so every time we need to increment it. Maybe just try to keep the likes in order of a power of 2 or power of 10. So only when that is it's meeting that, we'll try to increment it accordingly, so that we don't lose the actual value too, and also we are trying to drop all writes at once. So just that was just one vague example, but we'll try to elaborate on that. So that's the rough intuition of this queue and shed. The fourth is basically batching plus aggregation, and this I think it should be, we'll try to batch writes mostly in kind of when we are looking for aggregate related queries and all analytical related queries. And hierarchical reducers is basically it's kind of complex approach, kind of a very edge case, which we'll talk about in case of the live commenting related use case. We'll discuss about that. So now let's try to elaborate on this first one. So vertical scaling and write optimization. So this one is basically first one to just blindly go and try to increase the hardware that we have currently for our specific server or database. So because we know at least we know the basic understanding that writes are bound by a disk input output, CPUs, capacities and network. So let's say we have our single server with DB 8 cores and 1 GB network interface card, and it roughly this capacity handles 1k writes per second. Assuming that we scale up, so to 200 cores, and so it handles like 50k plus writes per second. So that's like immediate way. Whenever we see this sudden pattern, the first measure that we can take, so that it'll help us buy time to actually think logic wise or algorithm wise or something in the code or something that we can really make it efficient or so. So that's the one thing, straight away simple way, just trying to upgrade our hardware. So here basically the only thing is we just need to be very careful with appropriate numbers that we do, like what is the writes or second, like ops, like math calculations per second, and so that understand the hardware which can support that numbers, and accordingly scale up things, because mostly really often helps us than we normally think. We might think this is a vague solution and all, but really it helps it to buy us some time. So that's like the vertical scaling, straightforward. And now this database choices. So here this is very important. So basically here we need to be very careful of what kind of system that we are designing, and try to choose the database that was built for that. So first we need to think in that direction. So is it write heavy on so then we need to think of like what are the databases that was meant to handle that kind of scenario. So for example here let's take an example of a Postgres versus the Cassandra. So assume like we have lot of writes coming in to our system. So instead of preferring Postgres, it's always good to go for Cassandra, because some of the traits of the Cassandra is basically it's only append-only log. So whatever the writes that it will be receiving, it will be appending. It's not like in place update like Postgres does. So this traditional B-tree, what it does, like assume like these are the some data that we have in our Postgres, and whenever I wanted to write, so first it tries to find some specific thing that we wanted to write or update or so it does basically in place update, and so looking for that specific thing and trying to update it. It's basically the turnaround time for is basically high, and as writes requests are more, so the traffic that we are receiving at scale is something this DB cannot handle. So that's the situation, like this append only log, we don't do any operations and all, so it will be quickly able to handle assume like roughly it can handle 10k plus writes per second, whereas like this is like 10 times less than what Cassandra can handle, which is 1k writes per second. So this is the only downside is basically this reads become slower, because that's a trade-off, because we know that write traffics are more, and this reads is something that we need to we can deal with that. So and this reads would be fast. So that is this first consideration, writes versus read. And so basically, like I said, optimizing writes usually cost this read speed and all, that's fine. And so that was one example of like the choosing the right databases. Should we go with the Postgres, B-tree, traditional, and then the Cassandra, append only log, and like that. So like that we have specify specific write optimized stores. Like if it comes to time series related stuff, we have like in InfluxDB or timescale DB, and log structure databases like the level DB, and column stores like we have ClickHouse, which can handle batch writes efficiently for analytics workload. So if we know this various options that we have for specific scenarios and all, if we have a rough idea of all of that, it will be easier for us to make a choice. So that's the the point is all about understanding the databases, and so that we can make a right choice for our specific application. So that's how we can handle writes properly. Now let's go to this second point, which is sharding and partitioning. So here basically assume like we have tried with our hardware upgrade and the database choice and all. Now basically assume like we have chosen Cassandra and some hardware which can handle 10,000 writes per second. So this we can basically handles one server can handle that many writes per second. Assume like we are receiving more requests, more than that, 10k plus and all. So that single server is something that cannot handle. So obvious thing is basically try to split it. So meaning had more servers of that kind. So that's where like the sharding is basically. So let's take an example of simple things that we normally use mostly in any of the application, which is Redis. So Redis cluster. So basically here what we do, so I'm just taking an example of Redis cluster here. So each entry in our Redis is stored with a single string key. So the key that we have, so these keys are basically hashed using some CRC function or whatever it is to basically determine the slot number. So slot number, this basically what do they help is helping us to maintain the mapping to servers. So this let's say I provide a key as a build, and using that hash function I get some 1 or 2. So I know now the slot 1 is mapped to server C. So this basically whenever now clients request this thing, so it will find this slot number and it knows which server to write to or so. So just simple example, now whenever I wanted to write a value to this, it hashes the key to determine the slot number and looks up the server responsible for that slot, and it will send this write request to or write accordingly to that server. So this basically what by doing this, what are we really taking help is basically we have spread our data like across this servers like server A, server B, and the server C. So that way like now each server can handle on its own, and we are not hitting the same server and trying to handle. And now the here basically the one thing we need to carefully decide is how do we choose a good partitioning key. So that is the thing that we should focus on whenever we try to think of sharding. So basically here how do we choose, and if by chance assume like we have chosen the wrong key, it's again taking back us to the same problem that we have, which is not able to handle the scales of writes that we are receiving. So that is what so let's just say that the good key, for example user ID is a good key. Let's say instead of user ID I decided to use the country as the partitioning key. So now the situation is I think straightforward. So now what happens is basically we'll try to end up with a lot of writes going to this populated countries like India, China, and so, and very few writes going to this very sparse countries like Highland and all and so. So this is again trying it's bombarding few servers and again becoming the bottleneck and throwing us back to the same problem that we have. So what if we choose the good key, which is hashing user ID? So like hashing user ID, it gives like 100 to 200 one server can handle, and other 300 to 400 number, let's say, that other server can handle. So this way it gets evenly distributed, and it tries to handle the traffic cleanly. So this is very important to understand like what is the ideal key that can really help us with this partitioning and all. Fine. So now that was like the horizontal sharding, so basically trying to split rows. Now let's discuss about vertical partitioning. So here the vertical partitioning, what it does, it tries to split columns instead of rows. So what ideally we do is like we separate different types of data based on their access patterns and the scaling requirements for them. So like instead of keeping all those columns in single table, we try to break it apart and how it is used. For example, so there so one table, let's say we have this videos table, ID, title, description, upload date, view count, like count, and watch counts. So this is like, let's say if it's getting hammered from all sides. Vertical partitioning, what really helps us is basically we'll try to split into multiple tables, these columns, and by patterns. So first we can have break it down to video or meta, so where it'll have ID, title, description, and upload date. So this basically, if we try to divide this by access pattern like this, same like video stats, I might break it into view count and like count, and video events like watch events and timestamps and all. So this way we try to split into specialized tables, and once we have now logically separated our data, this gives us a lot of leverage even to choose different databases which really suits for that specific case. So for example, here metadata, mostly it is write once and read many, so we can choose for standard or b-tree related stuff like Postgres and all, that should be able to handle. And here video stats, view count, and like count. So if we know that it is something like the write frequency is very high, so in that case we can choose some in-memory counters or in-memory database that really helps us with directly writing it memory instead of going into disk and seek in and seek out there. So same for video events. Since like it's a like kind of like watch events and timestamp, it's like append only that we wanted to choose. So this here again we'll have a choice to make the ones that it's optimized for, like time series related database and column or related database and all that stuff. So that way, if we try to partition in this vertical way, we'll have the choices to choose our own database. At the same time, operational complexities also is something rises, but that's a trade-off that we are going to make. So this is like the horizontal sharding and vertical sharding. So now let's jump onto the third the approach that we have, trying to handle the burst with queues and load shedding. So here basically the idea is simple. This queues is first one, write queues. Queues basically we try to use to decouple the accepting writes to processing them. So then that queue really acts as a helper to absorb any sudden spikes that we normally see. So assume so it's always the same. So we try to introduce the queue between our app server and the database. So what happens is basically whatever the app is trying to make a request, we try to add an entry into queue with some data that needed for our worker to pick up, and this whole heavy work will be delegated to our worker servers, and that worker will pick it up and does the heavy lifting for us and tries to deal with the actual business logic or domain logic that we have. Once it's done, it'll try to update our database for that specific status, and then this application server can directly check for the completion of the status from our database. So they are basically this is the thing. So mostly used to observe this short burst, but again here even in the case if queues become unbounded, meaning if writes outpace the DB for very long, the queue becomes really unbounded. So a lot of things will be piling up in a queue. So that is where again to handle that we try to use this load shedding approach. So this load shedding approach is basically that's also one of the strategy to thing. So here like I mentioned, if we are overwhelmed with a lot of requests, now we need to think of how can we drop any least useful writes to keep our system alive under even such heavy load situations, and also make sure at the same time we are not losing any data that is really valuable for us and for our users. So let's take an example here. So again these are all situation related and the system that we're trying to deal with. So let's take an example of Uber or the other scenario. So let's take an example of Uber. So we know that driver or the user driver, let's take an example, driver, he tries to report a location, and so we know that we are receiving requests like every 5 seconds or so. So it's okay that if you lose like few of the 5 seconds location updates to our database, until unless we have its is latest location write to our database. So meaning, so for example, less than 10 seconds since last update, we can just get rid of it. We don't have to like only during the high scenarios, high overload times, and greater than 10 seconds since last update, we can try to take that and update into our location db. So this way all the holder rights is something that we are trying to shed it and keep the latest one. That is what really matters for us. And this basically because ideally we need just last seconds of the previous update and not like more than that. So that's why like now we'll try to drop this, and this is one of the strategy to deal with that. So here basically because we know that anyhow the fresher write the latest location update is coming anyway with our real-time updates or whatever it is, so that we know it's coming. So we'll try to drop the before ones, and that's how we handle and keep the rest. So that's one of the strategy. That's like the example of what I mean for load shedding. So that's one of the example. So same way the other situations for analytic systems, we might drop the few of the impressions for a while to focus on more important metrics or more clicks and all like that. So it varies application to application, and that's where like we need to make some serious decisions based on that. So that was like the shedding. So now the fourth approach is basically batching and hierarchical aggregation. So here first let's talk about this at the application layer. So idea is simple. What is this? Basically we'll try to buffer many writes into one bulk write. So that's like let's say we are receiving 100 writes, so I'll just try to maintain it in my memory or so, and once I hit that number, I try to do that all 100 writes at once into our database. So that's like this is basically chosen when our app isn't basically the source of truth, mostly in kind of like situations of the analytics or so. So for example, let's say like we have some consumer or analytics consumer or other things as a consumer for our Kafka topic. So this like assume like it does some logic or business domain application or so, and it does some processing, and then it writes to the database. So it's consuming the stream, and it is doing something. So here what we do now is basically we'll try to batch up the writes before we send them to the database. So this way like I try to batch write 1, write 2, write 3 till n, and I do just one bulk write to the database. So even here if the application crashes, we can reread from this the Kafka topic, and this ensures that we haven't lost even any data. So and yeah, this is the thing. So basically now we have reduced 100 writes to one round trip, and okay, and before even I mean flushing into the database, like I mentioned, you will try to reread Kafka and again do the same thing. So that is the thing. And now the application layer is something that I discussed. Now intermediate processing is the another option as well. So here this is basically what it helps us is basically it's a middle service. Here it tries to helps us tallies events like over a window and then forwards that one update per key. So like to understand here, let's say we have like like batcher or so for our post or video or whatever it is on our platforms, and let's say like this we have the Kafka like events the topic or so. So let's say for one video option A as like the clip 4, option B as like clip 5, or like some other guys like the same clip 4 and all. So now we are receiving events like this. So this like batcher, what it does is basically this tries to keep the like count for that specific clip or video. So we know that from now here this events clip 4 has 2 likes and clip 5 has 1 like. So here ideally we'll try to show the number of likes or comments also for specific post or video on platforms, mostly not like who has liked and all. Mostly again that will be another, like once user is trying to view that specific video, then we might show all those details, but mostly in a feed and all we'll just try to show count. So here the count is what really matters for us. So here this like batcher can help us to keep this like count events, and once we have this for this clip, and so we are trying to do update to the counter for that video, instead of doing for every time a person is liking that clip or so this way basically, like I said, over a time of window, let's say 1 minute or so, like that, in 1 minute whatever likes has been received for that clip, we do at once in that window. So let's say like we have 100 likes in that window, so then we do 1 write instead of 100 writes to that specific event. So basically again this only helps this events are coming in that window, or else again it falls back to same rights whatever we have. So but that is the this intermediate or the processing is something that we can introduce like this, trying to understand the window patterns and see if we can reduce the writes to database. The idea of any approach is basically trying to reduce number of writes to database. That's the thing, simple. So that's the batch and aggregations, and this now that was at the intermediate processing, and we saw at the application layer. Now let's take a look at the database layer. So basically most databases basically they have configurable options, for how often the writes are flushed to disk. So as an example, let's take Redis default configuration for that is basically it will flush writes to disk every 100 milliseconds. So that means, let's say if we have 1000 writes in single batch, we only write to disk 100 milliseconds after the last write. So the idea is basically we can configure that, and also at that layer as well, if we wanted to reduce number of writes to our store, and increase this based on this, so that even the writes are taken writes hammering our server is something that is taken care. So like last option at the even at the database layer is something that we can work on. Fine. So these are all examples of Redis has and Postgres has write ahead log batching and all those things. So here again disk becomes the bottleneck. So that's the thing. Fine. So that was all about the batching and all that stuff. And now let's try to discuss this hierarchical aggregation. This is the last strategy. So in basically this is kind of complex things, and it's also extreme case, like let's say high volume situations like analytics and stream processing. If you see those kind of situations, we really don't need to store individual events, and instead basically what we need is aggregated values or views or whatever it is. So this, we know that if it is aggregated things, that can be easily built up incrementally. So that is where this hierarchical aggregation is something really helps us in processing data in stages and reducing volume at each of the stages in that process. So the example, let's we have video streams and all that stuff. So in that situation, viewers they can comment and then like comments on that video stream also. So whenever a specific viewer also performs this either of these events, then all other viewers or whoever are viewing it should be notified of it. So you get the situation, right? So this basically creates very ugly situation for us if there are I assume millions of viewers and millions of users are writing, and now all of the writes needs to be sent to all of their pages. That's where millions write, and every write must reach millions of pages. So this this is the situation. So everyone is trying to do like events or like commenting and all those things, and this is our app, and then and this is something that again we need to broadcast it to all other viewers who are viewing. So this is the situation. So here first step is basically how do we deal with this kind of situation is we can try to simplify from both standpoints, and let's see, like, one step at a time. So first step is basically we can add broadcast nodes, which is a fan out. So here we know that all our viewers are basically looking for the same consistent view. So basically they wanted to see all the latest comments and counts associated with them, like likes or so, and so. So here the idea is basically we will try to assign these viewers to a broadcast nodes instead of directly to our root processor. So this way now instead of now this root processor writing independently to each of this viewer, now we can just write out to this broadcast nodes, which that will help us forward the updates to that respective viewers. So that's the idea. So now basically what we have reduced is basically instead of writing it to, let's say, n viewers, we are only writing it to m broadcast nodes. But again we have a we are taking care of the broadcasting thing, that's fine. Other side, now we have this problem. How do we deal the same way with the incoming events from all the viewers? So same thing we can try to handle in the similar way, this the fan in thing. So here what we do, this we'll try to again introduce some write process here. This what it does, it will try to aggregate writes over that window, what I said, like let's say 1 minute window or whatever it is, and we'll try to let that viewer connect to this specific write processor, and then that will be sent to the root processor, and then that will merge all of them and again broadcast it to the respective nodes. So here basically how do we choose which viewer goes to which write processor is basically can be chosen based on the like ID of the comment, or like for example likes the comment ID, it is liking or so. Like I'm just stating here, we are talking about an example of live video streaming for comments and all. So now if we choose based on that ID of the commit, so if that specific event is happening for that comment will be written to the specific processor. Same like for other comment it might go to the other processor. So this way it will know which write processor to reach it, and then handle it over a window, and then send it to root processor, and then this will merge all of it and broadcast accordingly. So this by aggregating this data with this write processors, and again disaggregating with this broadcast nodes, we now have drastically substantially reduced the number of writes that we need to do for each specific user. I know this basically introduces some latency by adding steps in between root processor, but like that's the actually the the core of the hierarchical aggregation, and that it really helps and helps us with handling such scenarios. So these are like all the approaches that we can adopt to solve this scaling writes problem, and depending upon situation try to adapt the one which really helps us solve the problem. These are the ways that we can think of. Now again, like I said, when to use all of these approaches and all that we discussed. So it is always the question falls back to like try to identify which is very write heavy endpoint, and then do some back of the envelope estimations like writes per second versus capacity, and only if it's we see it's a scaling writes problem, then deep dive into one of the approaches that we have discussed above. So for example, with millions, let's say, posting, we will definitely hit write limits. and then you need to check what's the throughput, and if that is the case, then we need to deep dive into one of the approaches, any of the approaches that really makes sense for that specific system, whatever we had discussed about. That's like falls into this scaling rights pattern. And so basically, like common scenarios is something like this. Most social media platforms like Instagram or what social, so there they try to use sharding techniques, like sharding by user ID and vertical partitioning, profile, post, analytics, and news feed. This they try to they try to adapt this fan out and fan in approaches mostly for popular accounts or so. And for search, this write heavy pre-processing and partitioning plus batching and all, they try to adapt these techniques. Live comments, which I just specified, the hierarchical aggregations and all. So these are like scenarios and where one or two approaches from this pattern is something adopted and then built to tackle those rights scenarios. So fine. And when not to use, basically do not try to scale prematurely, just try to do back of the envelope estimations, throughputs, and so here basically this is very important to understand when it is not necessary. So this basically, it really comes up with trade-offs. So like assume like you're just choosing this approaches as strategies that we just discussed. It'll assume like you went with queue. This comes with trade-off is basically eventual consistency and delay, and also that introduces that problem. Again, if you're choosing partitioning, the read path may suffer, and again you need to lay more focus on that. And if you choose a batching, it'll add latency and moving parts and all. And so always see that you don't really over engineer the stuff and all. I know we always try to end up in that situation, but better to avoid and mitigate wherever we can. And if it's a small scale, just stick with single dB, and that should be able to help with us. So because if you try to introduce this any of these approaches, instead of creating solution for our problem, it itself will become the problem for us. So that's the thing. So now let's just common scenarios, like for example, how do we handle resharding, like when we add more shards and all. Let's say like I try to increase 8 to 16 or like 16 to 32 and make sure that we don't have a node no downtime. How do we handle this kind of like things? So that's where like we'll try to do an dual write to old plus new. And so what do? We try to do like multiple dual write to old shard as well as a new shard, and we'll try to read from the new one, and in the background processing we'll try to backfill from this old shard, and once we are done, we'll try to cut over, and this new reader will be reading it from the new shard. So that's like trying to do dual writes, and this way like we make sure that no data is lost, and also like and there's no downtime, and then we drop the old shard when backfilling is done. So that's like one of the usual migration, gradual migration to handle that kind of scenario. And now basically, and another scenario is like when we have a art key, that's too popular for even a single shard. So that's again we'll try to break down that key into multiple sub keys. So basically here, so we'll try to split that like this is popular, like celebrity problem, like most popular accounts, like for viral tweet or viral video, or like which is receiving billions of views or something like that. So that's like considered as an hard key, and then we'll try to again use the sub key and try to spread across multiple shards, so that the traffic will be distributed to that respective shards. So here the idea is that we'll try to split into k sub keys, and now basically now if writes is something, it is will be taken care. For reading, again we need to sum all of this the sub keys whatever that we have. I'm mostly like writing the likes or comments or something that we split it. So for example, some reel is going viral, so likes we can split it something like this: additional sub keys 0, 1 or 2, and those things. Only thing is again to read back all the likes for that specific this reel, we need to again sum all of that. But again, this is a trade-off for read thing. So because now if we split this, now each shard just takes 1/k of the write volume what was taken by this single shard. So that's the thing. Uh, and also that was like, splitting the key thing, and the splitting key dynamically. That was like we decided that was the going to be harder, so we split it statically also. But the other situation is also like, we can break this hard key into sub hard keys, sub keys, like based on like, we are seeing some pattern whether keys odd or not. For example, like I said, for viral tweet or so, we might split across like, let's say 100 sub keys and all, each handling 100 likes or 10k likes or 1k likes. When reading, we aggregate those counts from all sub keys. So basically both of these approaches, whatever we just mentioned, so they mostly work for the metrics that can be aggregated, like, likes, views, counts, balances, but they don't work at all for anything that must remain atomic, or for example user profiles. So this is something we need to choose and adopt for the ones that really suits for. And here this writer will track which is hot, and then if it's a cold, we'll just keep it in one shard. If it's hard, we'll try to do this sub keys split. So this is again we might have some logic within that time span, how many events it is receiving, or is it like above the threshold that we have, then accordingly we can dynamically split by keys and all. So yeah, so that's the thing, the how we do this handling of these hard keys and all dynamically as well. So to conclude, this is basically only choose when it really solves our problem. Until then, stick with simple way, and and do not try to complicate and choose any of these approaches. So because the key insight for any of the approaches basically trying to reduce throughput per component whatever we have in our system. So and basically, and make sure that each one can handle the manageable load and all. So that should be our goal and the insight whenever we are trying to discuss. This is all about the scaling rights.